Have you ever felt the hair on your arm stand on end when you were close to something with a strong static charge? That's the electric field at work. An electric field is an invisible force field that surrounds any object with an electric charge. This charge can be positive or negative. The strength of an electric field depends on the amount of charge and the distance from the charged object. Think of it like gravity. A more massive object has a stronger gravitational pull. Closer to the object, the force is stronger. Electric fields are important in many areas of physics and technology. They are responsible for the flow of electricity in circuits, and they are used in devices like capacitors and transistors. Without electric fields, our modern world would be a very different place. We all know magnets. They stick to your fridge and can be surprisingly strong. But magnetism is more than just fridge magnets. It's a fundamental force of nature, just like electricity. In fact, they are deeply connected. A magnetic field is a force field that surrounds moving electric charges. This means every time an electron zips by, it creates a tiny magnetic field. In a bar magnet, countless electrons are spinning in the same direction, their tiny magnetic fields combining into a much larger one. Just like electric fields, magnetic fields have a direction and strength. They can attract or repel other magnets, and they can also influence moving electric charges. Imagine shining a light through air, then through water. The light bends, right? That's because light, an electromagnetic wave, interacts differently with different materials. The same goes for electric and magnetic fields. When electric fields pass through a material, they interact with the atoms within it. Some materials, like conductors, think copper wires, allow electric charges to flow easily. Others, like insulators, think rubber gloves, resist this flow. Magnetic fields also interact with materials in unique ways. Some materials, like iron, are strongly attracted to magnets. Others, like wood, barely react. These differences come down to how the atoms in the material respond to magnetic fields. We've seen that materials can change how electric and magnetic fields behave. But how do we measure these changes? That's where permittivity and permeability come in. Permittivity, symbolized by the Greek letter epsilon, tells us how easily an electric field can pass through a material. A high permittivity means the material allows the electric field to pass through easily, like air. A low permittivity means it resists the field, like rubber. Permeability, symbolized by the Greek letter mu, is like permittivity, but for magnetic fields. A high permeability means the material is easily magnetized, like iron. A low permeability means it's hard to magnetize, like wood. These two properties are essential for understanding how electromagnetic waves, including light, travel through different materials. Section 5. Susceptibility and conductivity. How much can a material take? We've talked about how materials respond to electric and magnetic fields. Now let's get more specific with susceptibility and conductivity. Electric susceptibility, often represented as K, tells us how easily a material can be polarized by an electric field. Polarization is like temporarily separating positive and negative charges within a material. A high susceptibility means the material polarizes easily, like water. A low one means it doesn't, like air. Magnetic susceptibility, or KHM, is similar but for magnetic fields. It tells us how easily a material can be magnetized. For instance, iron has a high magnetic susceptibility, while wood has a very low one. Electrical conductivity, denoted as sigma, measures how easily electric current can flow through a material. Conductors, like copper, have high conductivity. Insulators, like rubber, have very low conductivity. Section 6. Maxwell's equations. The rules of the electromagnetic world. Just like we have laws of motion in physics, we have Maxwell's equations for electromagnetism. These four elegant equations, developed by James Clerk Maxwell in the 19th century, describe how electric and magnetic fields are created and how they interact. First, Gauss's law for electricity. This equation tells us that electric charges create electric fields. It's like saying that where there's smoke, there's fire. Where there's an electric charge, there's an electric field emanating from it. Next, Gauss's law for magnetism. This equation tells us that, unlike electric charges, there are no magnetic monopoles. In other words, magnets always come with a north and south pole. You can't have one without the other. Then, Faraday's law of induction. This equation describes how a changing magnetic field creates an electric field. This is the principle behind electric generators, where rotating magnets create electric currents. Finally, Ampere-Maxwell's law. This equation tells us that both electric currents and changing electric fields create magnetic fields. This links electricity and magnetism together, showing they're not separate phenomena but two sides of the same coin. Section 7. Boundaries and barriers. How fields behave at interfaces. Imagine throwing a ball at a wall. The ball bounces back, right? Something similar happens when electric and magnetic fields encounter a boundary between different materials. These are called boundary conditions. For example, when an electric field crosses from a material with one permittivity to another, the field lines bend. This is similar to how light refracts when it enters a different medium. Similarly, magnetic fields follow specific rules at boundaries. These boundary conditions are crucial for understanding how electromagnetic waves, including light, reflect and refract at surfaces. Section 8. Electromagnetic waves, riding the waves of light. Light, radio waves, X-rays. They all belong to the same family, electromagnetic waves. These waves are disturbances in electric and magnetic fields that travel through space at the speed of light. Imagine holding a jump rope and flicking your wrist. A wave travels down the rope, right? Electromagnetic waves are similar, but instead of a rope, they are disturbances in the electric and magnetic fields, propagating through the fabric of space itself. These waves carry energy and information, and they are fundamental to how we experience the universe, from the warmth of the sun to the colors of a rainbow. Section 9. Plane waves in a vacuum. Surfing the cosmic ocean. The simplest type of electromagnetic wave is a plane wave. Imagine a perfectly flat ocean wave with its crest and trough extending infinitely in all directions. That's a plane wave. In a vacuum, where there's no matter to slow them down, electromagnetic waves, including light, travel at the speed of light, a fundamental constant in physics. This speed is incredibly fast, approximately 299,792,458 meters per second. Understanding plane waves in a vacuum is important because it forms the basis for understanding more complex electromagnetic phenomena, like how light interacts with lenses, mirrors, and other optical devices.